They are visibility and sharpness. Each of these two categories has two subcategories. Visibility includes brightness and contrast. Sharpness includes spatial resolution and distortion. And then under distortion, we'll have several other subcategories as well, like magnification, elongation, foreshortening. Okay? So make sure you do know these terms. Right? It's very easy for me to ask you something like, which of these is considered to be visibility? Which of these is considered to be sharpness? Right? Which of these does not belong? Does that make sense? Right? So make sure you are familiar with these categories, with these groups. So let's first talk about visibility. And we are specifically going to talk about brightness. Brightness is just how much light is emitted by our monitor, right? Or how much light is emitted by our screen. So if the image is too bright, you can't really see things properly. If the image is too dark, you can't really see things properly. Right? You need a good balance to where you have proper brightness. Right? Not talking about lungs being black and bones being white, right? Because that's contrast. But we're just talking about the whole image is either too bright or the whole image is too dark. Right? That is brightness. And so brightness is connected to our dynamic range. Remember, we talked about this in the previous chapter. Our dynamic range is the range where we can capture our exposures, where we can properly capture and display our exposures. So if you use the right number of X-rays, you get a good image. If you use too few X-rays, your image is going to be white, right? If you use too many X-rays, your image is going to be black. And the range of X-rays you can use before this happens, right, that is your dynamic range. With film screen, you can't go very far from that perfect exposure before you get too black or too white. So too black or too white. But on digital imaging, you have many more options for exposures before you end up too black or too white. It's a wider dynamic range. You can capture a bigger variety of brightness levels. Okay. So, if our exposure is too low, if we do not have enough X-rays, we call that underexposed. Right? Low, under, right? So underexposed. Too high, we call it overexposed, right? Exposure, right? So high, over. So overexposed, how does that image look?
White.
Black.
Oh,
Black. Underexposed, how does that image look?
White.
White. Right? So too many X-rays, image looks too black, overexposed. Too few X-rays, right? Not enough, looks white. Yes?
Can we go back to the last slide on that note? So the image on the leftmost image is quantum noise?
So let's just talk about exposure. Overexposed or underexposed?
Under.
Underexposed. Not enough X-rays?
Yeah.
Looks too white. How about down here on the other end?
Over.
Overexposed. So it looks too black. Now, here we have quantum noise or quantum wattle. This is an artifact which shows up if you do not have enough X-rays. And we'll talk about this in a slide further down the line. So quantum noise is associated with underexposure. Right? If you have it underexposed, you are likely to see quantum noise. Overexposure is associated with saturation. you gave too many X-rays to your detector has gotten so many of them that it's become saturated, right? So saturation goes with overexposure. Okay? The detector just can't take any more X-rays, you gave it too many.
Can
Yes?
detectors that become too old or broken start causing saturation?
So this has to deal, once again, with dynamic range. So usually the issue isn't going to be that the detector has gotten too old that its dynamic range has decreased. This is just more like comparing, looking at like film screen, right?
Okay.
It's like film screen, you used slightly too many X-rays, too bad. It's saturated now, overexposed, image looks too black.
So now we don't really have these exposure errors. This is
So-
only for
You would need to do something very, very bad to end up with these exposure errors, right? What do I mean by really, really bad? For example, who's done portables? Right. Anyone have to do a portable knee? Okay, a few of you. So, on those Carestream machines, the portable knee, I believe the default setting is 60 kbp 8 max. That is with the assumption you are using a grid. Most techs do not use a grid for the knee when they do portables. If you leave it at that exposure setting, you will cause overexposure, right? And so that's why a lot of times you will see techs, when they select the knee, they'll go to the screen and they will decrease their exposure factors. They'll drop their mass to avoid overexposing. Okay, so right, really common is just using a grid technique when you don't have a grid. It causes overexposure. Maybe setting up an abdomen technique and then shooting a chest, overexposure. Okay. Or, and this is something really bad that you haven't really gotten into yet, selecting the wrong AEC will cause overexposure. What AEC is, it's a way for us to ignore having to set our own exposures. Rather than us knowing what KVP and what mass to use, we use AEC, we set a KVP, we set our MA, and the computer will decide how long to expose for. So the computer will determine our mass. How does it know how long to expose for? It's got a detector behind the patient. It measures how many X-rays are passing through. Once you have enough X-rays pass through, it cuts off your exposure to give you the perfect brightness. However, what if you accidentally choose the table AEC while you're doing a chest X-ray? So you shoot your chest X-ray, but the table AEC is there waiting. It's like, when am I going to get some X-rays? Right? I'm waiting for X-rays. Once I get enough X-rays, I'm going to turn off this X-ray exposure. But I'm not seeing any X-rays. Meanwhile, the wall is just getting blasted by X-rays, right? But the YEC is like, well, it's not my job. You turn on the table AEC, so it's his job to wait for X-rays. Are you shooting any X-rays at the table? No. Is the table AEC going to ever get enough X-rays? No. So what's going to happen? It's going to have a really long exposure time, and you are going to overexpose your patient. And it's just going to look black. It's going to look like that at the end. Right? So be careful. Be careful with your equipment. Know how to use it properly. Okay. So we need a way to describe the amount of exposure to that IR. Right? If we have the proper amount of exposure, we will get a good brightness. If we have an improper amount of exposure, our brightness is either going to be too low or too high. Right? It's too low, it's too dark, overexposed. Too high, too white, it's going to be underexposed. So we have things called exposure indicators. You may have seen this at clinic. For example, if you are using your CR systems, right, with these cassettes where you have to run them in the processor, they use something called S value. sensitivity value. If you are working on a carestream machine, they use EI or EXI. Okay? If you are working on some of the other equipment, it may be some other type of exposure indicator. Right? The type of exposure indicator depends on whichever vendor you are using, which company made the equipment. And they will tell you this is the range of exposure indicators which tells you got a good image. As long as your exposure indicator lands within these two numbers, as long as it's between these two numbers, that means you did a good exposure, you will have good brightness. Does that make sense? So, for example, with S values, when you shoot a hand, you want your S value to be between 75 and 200. You shoot your X-ray, it says 169. Is that good? Is it between 75 and 200? So, good X-ray. Great job. Good KVP, good mass. You shoot an X-ray. It is 80. Is that okay? Yeah, between 75 and 200. Still okay. You shoot an X-ray. It says 270. Now it's outside our range, isn't it? It's no longer between 75 and 200. So, outside the range, now we know we either overexposed or underexposed. Which one was it? For S values are inverse. S value is too high, you underexposed. S value is too low, you overexposed. Everything else is direct. So with your EXI or your EI values, let's say your perfect EI value is 1600. You shoot it at 3000, that means you overexposed. Okay? S value is the one that is inverse, it's flipped. It's kind of funky that way. And you'll learn, and you'll discuss this more in Mr. Donahue's class as well over the summer when you start doing image evaluation. Okay? So, any questions about this here? Right. Over here, right? Here's our example of S values, right? S value of 200 for this exam gives us our optimum exposure. S value is too high, means underexposed. S value is too low, means overexposed. But everything else is direct. All of these other ones are a direct relationship. So we have REG, we have log mean. So this is actually an L. This is a lowercase l. It's LGF, log mean. And then we have EI and EXI for our exposure index. Sorry. Okay.
Mr. Phung,
Yes.
you said if it's
LGF.
if it's too
Oh, sorry. Yes. EI and EXI. Yes, sorry. Yes,
you
Jimmy.
said if it's too high, it means you're overexposed. Is that? Are we talking about the S value?
Only that one.
So for S
Yeah.
value,
Uh-huh.
too high is underexposed,
Under. Okay.
too low is overexposed. And you can see that in the chart over here on the right.
Okay, thank you.
But for everything else, reg, log mean, EI, EXI, if it's too low, if the number is low, it's underexposed. If the number is high, it's overexposed. These are the ones that follow your, what you would expect, right? S value is the one that's kind of weird. Yes?
S
John?
value ranges from 0 to 1000.
It can go more than that, right? It's just your normal ranges will be somewhere around 75 to 600, depending on the body part and what equipment you're using. So to give you some examples, for a chest X-ray inside the room, 72 inches with the grid, everything is set up inside the room. S value is expected to be between 200 to 600. On the other hand, you try and do that thing tabletop, outside the bucky, cassette, 40-inch SID, right? 85 kVp, 3.2 mass like a portable. Now your S value range is between 100 to 400. You do an extremity, 75 to 200, right? So not a chest anymore, but extremities, 75 to 200. So it just depends on the anatomy and how you are doing it. So there will be charts, there will be information telling you that for this equipment, these are the ranges we expect, doesn't matter which one, but these are the ranges we expect for each kind of exam. Okay? So that way, that's how you will know if you are in range or not. Does that make sense? Right? So when you start working, right, and they're training you, right, first thing you should do is, all right, here's my equipment, learn the buttons on the equipment, and then also learn your exposure indicators. Know what the correct ranges are, so you can tell if you are overexposing, underexposing, or optimally exposing. Good? Yeah. All right, great. So, because we use digital imaging nowadays, we do have the option of changing our images. Right? We can make our images brighter or darker. Right? In the old days, the film, what the doctor got was what the doctor got, right? They just have it, they stick it on their light board, and then they just have to squint at it and hope that it was the proper brightness. But now we can change it. And so the process of changing the brightness deals with the window level. So brightness is about leveling. Okay, so level deals with brightness. Make sure you remember this one, because in just a few slides we will talk about contrast. And contrast is not leveling, contrast is windowing. So brightness is leveling. Okay, increasing the window level increases brightness, decreasing the window level decreases brightness. Okay, and we call this post-processing. So we have the image already. We're changing the image after the fact. We've gotten the picture, we are editing the picture. That is post-processing. You may have heard like people say, oh, I'll just take this video and edit it in post. Right? Same idea, post-processing. Have your raw data, you're now going to change it up. So, with brightness, right, we're just taking this and changing where we are on this level, right? We're going to increase our window level, make it more bright. We're going to decrease our window level, make it more dark. And so, compare brightness to contrast. Remember, brightness is the overall brightness of the image. How white is the image overall? How black is the image overall? But contrast is about differences. What's the difference between your white and your black? Is it really white and black? Or are you more dealing with gray colors, shades of gray? So, remember, why do we have contrast? What is that special terminology? What gives us our contrast? It is differential absorption. Very good. Differential absorption. So, because of differential absorption, some places will be darker, some places will be whiter. Right? If two tissues have the same amount of absorption, they should have the same brightness, right? If two tissues have different amounts of absorption, they should have different amounts of brightness. The one that absorbed less should be darker. The one that absorbed more should be brighter. That is how contrast works. So, high contrast, big differences between their brightnesses. Air, dark, bone, bright. Big difference, high contrast. Okay, low contrast, very similar levels of brightness, hard to tell them apart. Got muscle, kind of gray. Kidney, also kind of gray. Hard to tell them apart on an X-ray because they're both similar colors, similar shades of gray. Right, so, with between these two images, which one would you say has higher contrast?
One on the left.
So which one has bigger differences between the objects? Which one has the objects pop out more at you?
One on the right.
On the right, sir.
That's right, the one on the right. Right? This one almost looks like washed out. It looks almost faded, right? All the colors are kind of the same.
Blended.
Here you've got bright colors, dark colors, you've got bright colors. Here you have kind of dark, here you have kind of bright, right? So bigger differences here on the right side. So higher contrast on the right. Does that make sense? Good so far? Okay. Which one is high contrast?
On the right.
On the right.
Right?
Yes.
Why this one on the right?
Because it's black and white. That was our difference.
There's a really bright color.
Good. Good. More black and white, right? If the structures pop out more, it's more obvious where one structure starts and where the other where one structure starts, where one structure stops, right? You can see the edges more clearly. So yes, this one on the right is your high contrast. So, when we talk about contrast, because these shades of colors, right, these blacks, whites, and grays, are based off the anatomy, are based off differential absorption, we call this subject contrast. Contrast caused by the anatomy, right, our subject. So, if we're looking at the chest, right, the lungs are naturally going to be dark because they're air-filled. The spine is naturally going to be white because it's bone. So the anatomy has this natural contrast. It has this built-in high contrast. Does that make sense? Right? So in the chest, right, ribs and spine, how should they look? White. Air-filled lungs, how should they look?
Black.
Black. The heart, how should it look?
Blurry.
Well, how does the heart look on?
Whitish, grayish.
Whitish gray, right? The heart is still pretty bright. Okay. So big differences in our contrast. What, right? It's black, it's white. So high subject contrast. The anatomy itself has big differences in the differential absorption, so it has high subject contrast. Right? This is innate, it's built into the anatomy. Does that make sense? It's not something that we can adjust, right? I can't go into the patient and change the subject contrast. I can't go to the bone and be like, hey, I need you to stop absorbing so many x-rays, right? The bone just naturally absorbs more x-rays, air naturally transmits more x-rays. So that's subject contrast. Yes, Johns?
That's the atomic number.
Right, so atomic number, tissue density, tissue thickness, right? These things that are just naturally part of the tissue are what give us the subject contrast.
What you said were examples of naturally high subject contrast.
So naturally high subject contrast, like bone, right? And air, bone versus air. Those have high subject contrast just because of how they are. Okay, so let's think of the abdomen now. Muscles, how do those show up in the abdomen x-ray?
Gray.
Gray. All right, how does like the liver show up in an abdomen x-ray?
Dark.
Grayish.
Light.
Gray. All right, how do other tissues show up, like kidneys?
Gray.
Gray. Colon?
Gray.
Depends, right?
Yeah.
That's feces, that will be
Depends.
dark.
Right, if it's got air, it's gonna be dark.
Yeah.
If it's got fecal matter, it's gonna be gray with some splotches.
What did I
Right.
try?
Yeah, so it could be air, could be gray, right? Could be dark, could be gray. Right, stomach, how does that show up?
Black.
Depends, right? Right, sometimes it shows up black, sometimes it shows up gray. Sometimes if you've made them drink contrast, right, it shows up white. Okay, but generally speaking, for the abdomen, those structures, do they have about the same color?
Yeah.
A lot of them do have about the same color. right? They have about the same amount of differential absorption. So, because they are all very similar, these have great low subject contrast, right? The anatomy just naturally has low contrast because of how it is. So that's what we mean by subject contrast, right? It's about the tissues themselves. It's about the anatomy itself. Nothing that we did. It's not our fault that the chest has high subject contrast, that the abdomen has low subject contrast, right? We can't change this. It's just a natural part of the anatomy. So far, so good? Okay. So, if we want to talk about contrast, right, we talk about colors. And so we talk about the grayscale, the range of colors we have from white to black. So if we have a low grayscale, we don't have very many colors. Okay. Or if we have a high grayscale, we have a lot of different colors. Right? That is how we would talk about contrast. How many colors are we dealing with? And contrast is also related to our bit depth, right? Our pixel bit depth that we talked about last chapter. So this is just the number of gray colors available to display. If I have enough gray colors, I could give the liver its own color. I can give the psoas muscles their own color. I can give the kidneys their own color, right? They each get their own shade of gray. But if I don't have enough colors, if I have a low bit depth, then I'm like, well, I've only got one gray. Guess I have to make the liver this gray, the kidneys the same color of gray, and the psoas muscles the same color of gray, right? No more differences between them. So, the bit depth determines how many shades of gray we have available to use. The more shades of gray we have, the better our contrast resolution, because now we can tell two structures apart. We can say liver is slightly brighter and psoas muscles are slightly darker, right? Two different shades of gray, I can tell them apart. Contrast resolution, good contrast resolution. On the other hand, if I do not have enough shades of gray, well, liver is one shade of gray, psoas muscles the same shade of gray, I can't tell them apart, so I have low contrast resolution. I cannot tell them apart. Right? Just like we discussed last chapter. Does that make sense? And that is in contrast to contrast. Right? So, contrast is just like, is it obvious? Like, how big are the differences, right? That is our contrast. So down here, not very many colors, big jumps in our colors, right? Big obvious differences. So high contrast, but if my liver is here and my psoas muscles are here, do I have two different shades of gray to display them?
No.
No, they fall under the same shade of gray, right?
Yes.
I add more shades. Now do I have a difference?
Yes.
Now I have two different colors that I can use for them, right? Up here, do I have two different colors?
Yes.
Yes, right? So low bit depth, short grayscale, not very many colors, low contrast resolution because I can't tell them apart. But high contrast because the things I do tell apart are very obvious. As I increase the number of colors, I increase my contrast resolution. Now I can tell these two structures apart. They actually have different colors. Okay? But as I go up, the differences become less obvious. It's harder to tell where one shade of gray stops and the next shade of gray begins. So I have high contrast resolution now, but I have lower contrast. Does that make sense? So we said that they are kind of inverse in that way. So, which one of these three has the highest pixel bit depth?
256.
256?
Yes.
Very good, right? Pixel bit depth of 8, right? Down here, only pixel bit depth of 4. Very good. Any questions about this one?
So how could you calculate 8 and 4 with 256 and 16?
In my head. No, I meant,
2 to the power of n you did.
so 2 to the power of n.
I see.
Or I just memorized it.
The
Or I just went through all of them in my head. You can believe whichever one you want. Maybe I just did this lecture so many times that I just have it memorized. Never know.
What a flex.
Yes, Sindhu.
Oh no, sir, I believe you.
Well, which one do you believe?
All of them.
Did I calculate that on the fly or did I memorize it?
You can calculate, I know.
You calculate.
Yeah.
like a table for that.
Maybe I just like the multiplication table, but instead of the bit that
Is that the stomach?
that I
No,
memorized.
that's the
All right. Do you need to memorize the bit depth table?
I need to.
No.
No, I'm saying you got kidney.
Just need know how to do
Billion and what?
2 to the n, right? That's all I need you to do. 2 to the n. Okay. So we were able to adjust brightness, right? We are also able to adjust contrast. What did we call adjustments in brightness? Window levels is dealing with brightness. So what did we call adjustments in that window level? Leveling. What do we call changes in contrast?
Windowing.
Windowing. So be careful. Make sure you know which one goes with which. So, Samantha, leveling goes with which one?
That goes with windowing. Oh,
Brightness or contrast?
oh, I'm sorry. That goes with
So which one does leveling go with?
contrast.
Leveling?
I'm sorry, what?
Sorry, which one does leveling go with? Does it go with brightness or does it go with contrast?
Brightness.
Brightness,
Okay.
great. And Carla, which one does windowing go with? Contrast, good. Reagan, what does contrast go with? Windowing. And Mansi, what does brightness go with? Leveling, great.
I see.
So, just make
Yeah.
sure you know that. Make sure you know which one goes with which. That's right. So now we need to be careful.
Even
Right.
more.
That's it. That's what I was
Brightness
saying.
is window level. That's why we have leveling. Contrast is window width. But we don't call it width thing. So we call it window width. Okay, so window width. Basically, right, if you think about this, right, sideways, right, width, how many of these colors are we actually going to be using? Right, am I going to make this a wide grayscale? Or am I going to make this just a narrow grayscale? Am I going to use all these colors or just a few of them, right? So that's why this is our window width. Does that make sense? Okay. So if we have a wide window width, if we increase our window width, that means we are going to have more colors. With more colors, we have less contrast, but higher contrast resolution. If we decrease the window width, we are going to have fewer colors, but those colors are going to give us higher contrast. Right? So, low contrast, high contrast resolution. High contrast, low contrast resolution. Does that make sense?
Hold up, Mr. Phung. Okay,
Sorry.
you said the first one
Uh-huh.
decrease, hold on. You said more colors,
Yes.
less contrast,
Mm-hmm.
higher contrast resolution, is that what you
Good.
said? Okay, that's all I need to know, thank you.
And just like leveling, windowing can also be done through post-processing. So, do you need an image on the screen before you can post-process?
Yes.
Yes. So what kind of image are we using for post-processing? The manifest image, right?
Ooh.
The image that you can see. Can you do post-processing with the latent image?
No.
No, all right. Good, so right now we're starting to combine knowledge from multiple chapters, right? Don't just think that latent and manifest was only chapter 8, right? We'll use this information in other chapters as well. Very good. So let's just see a real life example of post-processing. All right. And I'll just go with whatever my last image was, which I think was the baby. All right, so
Ah,
I've got a picture here, right?
that marker though. Mm.
Terrible picture.
So I am going to adjust
Jazz.
my
digital.
window level. For example, I can make the whole thing dark.
Don't do that.
I can make the whole thing bright. Do you see that? So I am adjusting what? Leveling, right. So does this fall under brightness or contrast?
Brightness.
Brightness, very good.
Yesterday was that baby's
So
birthday.
I'm moving up and down here.
Mm-hmm.
I can also adjust
One day.
my windowing. So I can do this. I can
Just
do
born
this.
yesterday.
Then you going side to side, right?
So right now I'm moving my mouse side to side because this is
Okay.
width, right? Window width.
It's her birthday.
So over here, right?
So that's the contrast here.
I've only got black and white, right? I can only see like bones and air. Do you see? That's right. So this is high contrast, but low contrast resolution. For example, can I see the heart? No. Can I see the liver? Can I see the stomach? Right? It all just blended together with the air, right? Or the rest of the organs. Right? So low contrast resolution. I can't tell those individual organs apart. Right? Now, now I can see the differences, right? Now I can see the differences. But it's not as big of a jump anymore between my colors, right? So the contrast is lower, but the contrast resolution is higher. Right? Over here in the chest, I've got black and I've got white, right? I've got these big jumps in color, right? So here I have high subject contrast. Over here, right, I've got liver, I've got muscles. Here I have many more colors, right? My jumps aren't as big, right? Like, for example, between this white and this black, big jump. But here, between this white and this black, not as big of a jump, right? So here, my subject contrast is lower. Because my subject contrast is lower, that means overall, right, my contrast is not going to be as big. The contrast is lower in the image. Does that make sense?
I have a question.
Yes.
Is that the S value you were talking about in the bottom? SZCW.
Great question.
Yep.
So down here, this is where you would normally see your S value.
Good job.
This is not actually an S value. This number actually is not correct. And the reason is because what kind of equipment did we use for this X-ray?
Cassette.
A portable. Is your portable using the CR cassette? No, you have digital portables, right? You don't need to worry about your CR cassettes. So, S value only goes to CR cassettes. It only goes to Fujifilm. So, the number we have here from CareStream, this is not an S value. This is some data that got improperly stored in the S value variable. So this is giving you no information about the S value. You can think of this as a bug, right? A computer bug. This is not the S value. However, let's see. Does anyone have an accession number from a clinic, like Valbona or
Strawberry. I got you.
I'm ready.
because I wrote down the S numbers. What kind of example?
Doesn't matter.
Oh, damn.
Anything more.
Let's do 172
172,
68
68,
089.
0, 8. All right. So,
Oh, look at that marker.
CR, Fujifilm. Now, this is an accurate S value. S value of 96. Extremities, I said, should be between 75 to 200. So, is this in range?
Yeah.
Yes. Let's take a look at our next image. What's our S value now?
98.
98. Is that in range? Yes. Okay. Next one, what do we have?
96.
96. Is that in range?
Yes.
All right, so great. All three of these fell within the correct S value range. That means, were these proper exposures? Yes. Do we have proper brightness? Yes. Can I still adjust this brightness after the fact?
Yes.
Yes. What is that type of processing called? Post-processing. And what two things can I do to it? Windowing and leveling. Great. So right, I can still grab this and I can change this up, right, however I want.
Oh.
Right? I can even do
Go DJ.
silly things like, right, if I really want to do it, that's right. I can invert.
Yep.
Wow.
Silly.
This is so much better.
Right? I can do that. Post-processing.
I like it.
You can do a lot of cool things with post-processing. For example, with post-processing, I can,
You can
for
like join
example, okay, I don't actually have it on the.
How does editing the contrast after you've inverted it change the image?
Same way.
Same thing?
Let's see. Do you have a chest X-ray?
Yes, sir. Do I have a chest X-ray? Let's
I
do
should have that. I'm the queen of that.
172 71 045.
I'm gonna be a master. That chest, 'cause that's all we had.
The master of chest.
Oh,
You click that.
where's the concentration?
That's not me. You see that marker?
Nah, you could
You
still
got
do
it.
that.
You see
It's
that?
like, you know what? I ain't gonna do
Okay.
that.
Of course I got the session number. I wanted to say that's it.
I don't have the option under CR. Interesting.
Oh.
Let's see. Anyone from, I guess, LBJ or Ben Top with the chest X-ray they can give me?
Anybody?
Charles?
Y'all
Mm-hmm. That's like the numbers.
Cindy?
He was from Midtown. Why she told me.
Yeah,
You
he
said
said-
LP there, but it-
Oh.
I thought you did.
171 46 150.
You said LBJ or what?
Or Ben Top.
Oh,
Alright.
well, then I got the top stuff.
So I've got this. So what other things can I do in post?
Chad.
I can sharpen up my image. For example, take a look at this chest X-ray here.
Okay.
And now,
You get it? I said the Chad.
do you see the change?
It's a chab, but it shouldn't be a chab.
Yeah, that's what
Right? You see how the edges suddenly become a lot sharper? Right? Compare this to the original.
Oh, yeah.
Right?
Wait, that's original?
This is the original. And now I can sharpen it up if I want to do.
Oh my god.
Right?
I was like,
I can make
what
this
is it?
really
I
sharp.
was gonna say, I thought I took off my glasses.
What other things can I do? I can invert.
Looks
right?
like it's calcified.
I can adjust my contrast. Right? I can oh, this surgical staples. I can take this and I can flip my image around, right?
Oh, yeah.
So a lot of things that I can do with post-processing. I just need to be very, very careful not to save these changes.
Oh, so if you save it, it changes physics to this?
Yes.
And will it
Make
say
sure it
Mr.
does
Phung?
no, right? Okay.
Yeah, they would know.
Oh. That would be bad.
After you discuss this, I have something to check with you. Leveling goes, I think I wrote wrong. Leveling goes with contrast.
No.
I wrote wrong, right?
Leveling goes with brightness.
And windowing goes with contrast.
Windowing goes with contrast. Alright, so do we understand the difference between brightness and contrast, leveling and windowing? You saw how that works on an image, right? We're all good? Okay, so once again, window level is brightness window width is contrast. Right? Make sure that you know which one goes to which.
Oh, 1 million.
And of course, the final key here is that it doesn't matter what your window level and window width is if you don't have a computer monitor able to show those colors, right? So we want to make sure that we don't cheap out on our computer monitors, and we have monitors with enough brightness and enough range to show the image properly. So over here I've got a, what is this, a Dell, I think?
You got the
HP?
right on.
All right, HP, what is this, like a 27 inch or something? 24 inch, 27 inch?
Yeah.
It feels like a,
It ain't on the back or nothing, on the side?
It's a rectangle, 27 by 24.
But you measure
oh,
it
you measure
by-
diagonally.
Yeah, we measure that.
I don't know, I'll just call this
24.
27 inch to make myself feel better that we have something nice. Okay, so we'll just pretend it's a 27 inch, right?
The result?
It's not
So
even-
maybe it costs like $200.
Oh.
Okay, actually, that's kind of expensive, maybe 150.
Uh,
Maybe they had a deal 100, right? So, radiologist monitors though, those things go for thousands of dollars per monitor. Why are they so expensive? Because they need to have the proper luminance, the proper brightness, and the proper range to display the images properly, to display all the colors, no matter what window level or what window width they are using. Does that make sense?
Mhm.
Okay. So we'll learn about those special monitors next semester in chapter 10.
So if I need a gaming computer.
You don't-
No, a radiologist computer is not meant for gaming. It probably does not have the refresh rate that you need. Right? They have different things they're looking for. Okay, so these two things we just talked about, brightness and contrast. What category did they fall under?
Right.
Visibility. Very good. Visibility, right? Brightness and contrast. Visibility. How do you see the image?
Yes.
So, then I.
Ooh. I'll beat up that remote.
It is beaten up. So, our next topic then is dealing with our spatial resolution and our distortion, right? So what was that? Louder? Sharpness. Okay.
Distortion is magnification.
So distortion deals with magnification, elongation, and foreshortening. Okay, so let's talk about spatial resolution, right? We talked about this last chapter as well, right? The ability to see two things that are really close together, but that are still separate, right? If you ever forget that, just remember that high spatial resolution, right? Low spatial resolution, okay? You can just console yourself with the fact that I am pretty much blind without my glasses on. Just like Charlie, exactly. We're blind buddies. The blind club. I see quite a few decent people with glasses. How bad are your eyesight glasses on?
I feel attacked.
Mine are like negative 7.
Hot here.
I'm bad.
2.7.
Cody had it
Okay, Cody, how about you?
I literally cannot see anything about them.
Ah.
Oh,
see,
my
like,
God.
anything farther than this is extremely blurry.
Mhm, okay. All right. So great. Well, we're in the same club. All right. So remember, spatial resolution, right? The ability to make out two objects is actually different rather than the same thing. Spatial resolution depends on the size of your pixels, right? We talked about that. It depends on field of view, matrix size, because that gives you the size of your pixel. How small are pixels? Pixels are measured in microns, which is the fancy term for micrometer. How small is a micrometer? 1,000th the size of a millimeter. How small is a millimeter? 1,000th the size of a meter. In other words, a micron is 1 millionth the size of 1 meter. Right? So you think about your millimeter, right? About this big. You take this, divide it into 1,000 pieces, and that is 1 micrometer. Right? So, very tiny. Now, that's not saying that pixels are exactly 1 micrometer, right? I'm just saying that they're so small, we need to use micrometers to describe them. Okay? They're so small that we have to describe them in micrometers. They're bigger than 1 micrometer, okay? It's just, they're so small we use micrometers to describe them. Because no one wants to say 0.0000067 meters. It's called 67 micrometers. Now, the smaller your pixels are, the more of them you can cram into the same area, right? They get smaller, you can fit more small things in the same amount of area. So this is called pixel density, the number of pixels you can fit into an area, right? For example, if you had a bunch of sumo wrestlers and you tried to fit all those sumo wrestlers into this room, right? You might be able to fit quite a few, but then instead of sumo wrestlers, you try to fit a whole bunch of children into the room, you can fit a lot more children than sumo wrestlers, couldn't you? Right? Why?
Because
They don't train it.
size is
Right, children are smaller. So the smaller they are, the more you can cram into a space, and so the higher the density, the more stuff you have inside the same area. And the more stuff we have in terms of pixels, the more pixels we have, the better our spatial resolution, the more clear the image will look. So over here, I crammed 256 pixels into the square. Over here, I crammed about 4,100 pixels into the square. Which image looks more clear?
they look similar.
Well, which one looks more clear? Which one can you see more details in?
The right one.
The one with more pixels, right? For example, I guess this is an olive.
Or
Do you see the olive over here?
no.
Yes, that's a martini.
So this is a martini? All right. Do you see the olive here?
No.
No.
Maybe-
Oh, it is the same picture of the same thing, sir.
It is the same picture of the same thing.
Also,
But
of course,
which one
this is more
more?
clearer, right?
That's right. This is more clear. Higher spatial resolution, right?
Yes.
So higher pixel density, higher spatial resolution, smaller pixels, like smaller pixel size. So if I ask you a question, and the question asks you, which of these has more pixels? Your answer is
The one on the right.
4096.
the one on the right, 4096.
So the
If the question asks you which one has bigger pixels,
252. The one on the left.
this one here, right? So be careful, right? There's size of the pixels and there's number of pixels. So just read carefully. Okay. Field of view, the amount of area covered, right? The amount of anatomy that we see. Matrix size, the number of rows and columns inside our image matrix. How many rows, how many columns do we use to demonstrate our image? So I'm looking at this much anatomy. For this much anatomy, I have so many columns, I have so many rows. That is our image matrix. The pixel size depends on field of view and image matrix. Okay? So it depends on your field of view, it depends on the matrix size. We also have one more new vocabulary term here, pixel pitch. The distance from the center of one pixel to the next pixel. So the distance between two adjacent pixels, center of pixel A to center of pixel B. Remember, pixels are square, so it doesn't matter which way we're going, right? The distance should be the same in all directions.
So I have a question.
Yes,
There's
you do.
no other pixel in between these two, sir.
No. You've got maybe this pixel.
One
Right.
pixel there.
So you've got one pixel here, one pixel here,
I see.
one pixel here. These squares are your pixels. once again, can a pixel have more than one color? No, right? Only one color per pixel. Good. So, new equation. Pixel size equals field of view divided by matrix size. So the size of your pixel is equal to the field of view over your matrix.
So that's gonna be in micro.
Right. So this would be in terms of micrometers usually. Right.
What's the sign for micro again?
It is a mu.
Okay.
So it looks like a fancy F.
It's like a
Looks
old
like
U,
it's an
right?
M with a tail. It's an M with a tail.
It's more like a U.
Or like a U. That's right. So because most computers don't have a mu key, right? People sometimes just use the U.
Like that?
It's the back of the M is longer.
Yeah,
Like a
tail.
cursive.
Yeah, kind of like that.
Yeah, like a, you're in a cursive kind.
Intercondylar eminence.
Curious, right? What a people looks like.
Oh. Yeah.
Like, it's like, yeah.
So I was right the first time.
It's more like a U.
You
not like
said the
Yeah.
tail was longer.
Oh,
It's just a
It's
U
long.
with a dot.
or sorry. So the initial line is long, and then the tail is off towards the. Sorry.
You good?
So yeah,
I thought the tail was long also, but I mean this is different.
yeah, it does look a little bit like a U. That's true. My fault. All right.
Rebecca, how's it go?
You watch me use?
So
Oh.
if the field of view is 400 millimeters and the matrix size is 1024, what is the pixel size?
0.39.
So I'm just giving you one side, right? So one side of the field of view is 400 millimeters, one side of the matrix is 1024. What is one side of the pixel? How do you do this? How do you set this up? Good, 400 over 1024, right? Just like that. And so, Shaheen, what did you get?
0.3907.
0.39, right? So we could say 0.39 millimeters, or you can say 390 micrometers, right? 390 microns. In fact, let me just go ahead and throw that in right now.
Appreciate you.
4.
It could it be 390 microns or decimal 390?
390 microns. Okay.
How's the difference?
0.39. How do you go from millimeters to microns? You take this, multiply by 1,000. The decimal point goes 1, 2, 3. 390. All right, let's try another one. If the field of view is 17 inches, which is, well, 431.8 millimeters,
Okay.
and the matrix size is 2048, what is the pixel size?
0.21.
How did you get 0.21?
431.8 divided by 240. Or 2040.
Good. All right, and then from here, you did that and you got
0.210.
0.21.
Then
Yep. So I'll go ahead and throw that over against that.
I'm just gonna leave it at that.
Actually, sorry, John, was it 0.211?
I think it was 0.210.
It was 0.210?
8, 0, 8. So I'm gonna
Zero,
do
eight.
it.
Oh, okay, let me write that then, sorry.
Oh, round up. Okay.
And what about the previous one then? It was 0.391?
0.
It was
I don't know if there was a number. Let me check.
390 it was.
3906.
0.3906, oh, got around that. Got around that. Alright, there we go. Now that's accurate.
So this is not millimeter, it's millimicron, sir.
No, this is millimeter. MM is millimeter.
But then 1,000 millimeter is a micron.
Correct.
I have a question.
Yes,
So
Jones.
on a test, you wouldn't expect us to convert inches to millimeters, correct?
Do I expect you to convert inches to millimeters? No. However, I do recommend that you know the basic conversion between inches and centimeters.
2.54, sir.
2.54. Right? You can round that to 2.5 to make things easy. And the reason I say that is because I had a real life scenario where I went to do a portable x-ray. And the portable x-ray was to check the breathing tube on a patient. They had just intubated the patient, so they had the tube inside, and they, after the chest x-ray, they said, can you take out the ruler on your portable machine and measure the distance from the carina to the tip of the tube? I'm like, all right, sure. I measure it. 10 centimeters. They're like, well, you know, it's supposed to be within 2 to 3 inches. Got a problem here because rulers in centimeters, they only know the inches measurement. So, what do?
Google.
That's right. If you know your conversions, you can take your 10 centimeters and like, oh, that's 4
Divided
inches.
by 2.4.
Right? You do your 10, divide that by 2.5, and you tell them, okay, it's 4 inches, right? Or you can be lazy and just stand there while they fumble with your phones and try and pull up a conversion calculator on Google. Right? But if you want to make yourself look good to the doctors, just remember, 1 inch is 2.5 centimeters.
I don't know, I'm not a math person. That's not my job.
Hold on, let me call up a reference.
Like, you know, I go to CT.
Alright. Can I phone a
I'm going to
friend?
CT.
Phone a friend.
That's not my job.
Yeah, I'm going to CT.
That's not my
You're
job.
going to see, I see. You're going to see.
Yeah.
It's still a good skill to have.
It is. More money.
That's not my
Yeah,
job.
I mean, you can voice type these days, like,
You never
Like,
know
hey.
when you're gonna go to a clinic and you're working and suddenly all the SID numbers are in centimeters and you're like, okay, I need to get a 40-inch SID. Why on earth is it only giving me 100 centimeters and 180 centimeters?
oh,
Be like, you know, I'm sick.
yeah. 100 is 40.
Or you detent it. So it's
Yeah.
like,
But what happens if there's also like an 80 centimeter one? Right?
the picture will be that
Hey
different.
Siri, 80 centimeters into 100, or dang.
Oh.
80 centimeters into inches. Don't fail me now.
That would be 31.5 inches.
31.5 inches. Thank you, Siri.
That was,
I didn't realize Siri. Okay. So,
that was a Siri.
He just said, okay.
Makes sense.
Yes, British Siri sounds better.
all right. So, spatial resolution, right? So, what did we say? Spatial resolution is connected to?
To the closeness of oh, it's
Matrix.
close.
Right? Sharpness, right? But what
FOV
determines
and
spatial resolution?
Matrix
size.
size.
Matrix size.
And the
Field of
FOV.
view. And those give you what?
Pixel size.
Pixel size.
And
So
the
in the
amount of
end-
pixels also.
Right, so in the end, it all boils down to the size of your pixels and the number of your pixels. The smaller your pixels, the more pixels you have, the better your spatial resolution. Okay, so as your field of view increases, right, as you go from this to this, right, matrix size is the same, field of view got bigger, right, your pixel size goes up, right, same number of rows and columns, but bigger field of view. Right, so pixel size goes up. Okay, the field of view gets smaller, right, going from here to here. Then your pixel size go down. Okay. Matrix size, right, if you go from this to this, right, of 2 rows, 2 columns, keep the size the same, but now 4 rows, 4 columns, my pixel size gets smaller, right? If I go backwards, 4 rows, 4 columns, take away some, end up with 2 rows, 2 columns. My pixel size got bigger, right? So that's how field of view and matrix size affect pixel size. Does that make sense? Field of view is directly proportional to pixel size. Matrix is inversely proportional to pixel size. Does that make sense? So field of view is directly proportional to pixel size. If field of view gets bigger, pixel size gets bigger. Matrix size is inversely proportional to pixel size. If matrix size gets bigger, pixel size gets smaller. So just know that relationship, know that general relationship.
So field of view is proportional to matrix size, but matrix size is inversely proportional to?
Field of view is directly proportional to pixel size. Matrix size is inversely proportional to pixel size. It's right here.
Oh,
Proportional,
so I wrote wrong.
directly proportional, inversely proportional. Okay, and so in order to talk about spatial resolution, we need ways to measure spatial resolution. And the way we measure spatial resolution is through a concept called spatial frequency. What is frequency?
Frequency is the amount.
The waves.
Right, so Joseph,
Amount
The number of
per
waves or something?
seconds of time.
right, so how many waves you have in a certain period of time, right? So just like Cody drew in the back there, right? The top one, right? You don't have very many waves in that length, so that's low frequency. The bottom one, you've got a lot of waves in the same amount of time, so that's high frequency. In this case, what we're using is, for those ups and those downs, we are using these black and white patterns, these black and white lines. These black and white lines are called line pairs. Right? So if spatial frequency is taking a pattern and repeating it multiple times, what pattern are we repeating? The line pair. So what is a line pair? It is one black line, one white line. Right? It's a pair, right? We've got 2 of them. One black, one white. So we've got a line pair. You just go black, white, black, white, black, white, black, white. You're repeating this pattern, right? We repeat this pattern. And the idea is to judge our spatial resolution, we want to see how thin we can make these line pairs while still telling them apart. Does that make sense? We want to see how thin we can make these line pairs while still being able to tell them apart. So, if I've got a big, thick black line, a big, thick white line, a thick black line, a thick white line, it's easy for me to tell that these are separate lines. It's black, white, easy to tell. But as they get thinner and thinner and thinner and thinner, right? I can tell them apart, I can tell them apart, I can tell them apart. But at one point, it gets really hard to start telling these apart, right? Like somewhere around here, it doesn't look like we have 5 white lines and 4 black lines anymore, right? Somewhere around here, they start to kind of like merge together. And that is the limit of our spatial resolution. We cannot show anything more detailed than that size. Does that make sense? Because anything smaller than that just sort of blends together with the neighboring objects.
So over here it's 1.25, is that level, sir? Where's the last you can see? The 5 lines.
Right, so we've got 1, 2, 3, 4, 5 white lines, we've got 1, 2, 3, 4 black lines, right? So line pair, line pair, line pair, line pair. Right? Here we can still kind of see 5, kind of. Here it's getting really fuzzy now. Not quite, We can still kind of tell, but it's reaching the limit. Here, we are pretty much done. We can't see them as separate anymore. Right, so our spatial resolution is limited to somewhere in this range, around 1.55 line pairs per millimeter. So our measurement is line pairs per millimeter. Does that make sense?
So, but you just said we can, at 1.55, we can still see the lines. So where we last can see the line is the
Limit of our spatial resolution. You can't see any more detail
after
than that.
that.
Correct. So what does this depend on? For example, this depends on our pixel size, right? If our pixels don't get any smaller than this, we can't see anything smaller than that. Make sense? Right? You can't see things smaller than 1 pixel because the pixel is the smallest part of your image. So pixel size plays a big role in this, which is why it's so important that if you want high spatial resolution, we have really small pixels.
So does that
Yes.
mean that at 1.55 if the pixels increases, then you'll be able to see the lines, thinner lines?
So yes, if in this image we could make the pixels even smaller, then we would be able to see
Even
more
thinner
detail.
lines and
Correct, even thinner lines. Good. So once again, what do we use to measure spatial frequency?
Line pairs.
Line pairs per millimeter. Very good.
Nice, very
That is a registry question. Make sure you know that. Guys, okay?
Mhm.
I see that.
My phone said to stand up, so that's why.
Okay.
It's
No,
like
No, I'm sorry.
around.
You're right. We should do some like calisthenics or something.
Yeah.
Exercise in the class. Just-
I've been voting for that for a while.
Oh, you got it.
Per millimeter.
All right. Yeah, remind me next time. Remind me next time.
the lines pair per millimeter is spatial.
Yes, spatial frequency, line pairs per millimeter. So we use this to measure our spatial resolution. Okay. So, something to keep in mind. You have a certain number of line pairs per millimeter. You can fit so many number of black and white lines inside 1 millimeter, right? So, I might be curious about, well, how thick is each line pair? Right? If I know I can fit this many inside 1 millimeter, I might want to know, well, how thick are those lines? And so, the thickness, the width of the line pairs are inverse to line pairs per millimeter. Right? So if I have 5 line pairs per millimeter, I take the inverse, right, 1/5, and that is how big my line pair is. It's 2.2 millimeters for each line pair. Does that make sense? So if I'm about 5 line pairs per millimeter, 1/5, my inverse, gives me 0.2 millimeters per line pair. Each line pair, the black and the white together, is 0.2 millimeters. Now, what if I only want to know the black line by itself? What do I do then? Divide by 2. Right? So each line, right, the black line or the white line, each of them is only 0.1 millimeters. Does that make sense?
So you're dividing the 0.2 by 2?
Mhm. Correct. This 0.2 you divide by 2. Because the 0.2 is black plus white. If you only want to know one of them, you divide by 2, right, to look at just one of them.
So the width of each line pair is inversely proportional to the line pair. Width of each line pair is inversely proportional to.
To the line pairs per millimeter.
Yes, you're looking at, yes, the other one is black and white. But if you
So,
just want to see the
Do we know where we got this
line.
0.2 from?
question, Mr. Phung.
Yes, Shamika.
Okay, you said if you wanna look at both lines, you divide, was it 1/5, or how did you?
That's right, 1 over your line pairs per millimeter.
And then if you're looking just for one, you divide by 2. Looking
And
for
then
one line?
if you're looking for just one line, you take your answer and then you divide it by 2. Right, so you first need to know how thick your line pair is. So no matter what, you have to get the inverse. Once you get the inverse, depending on if you want both lines or just one line,
Mhm.
you might need to divide by 2. See, I see some confused looks.
Oh, yeah, you gonna get them.
So,
Okay.
all right, over here,
Okay.
let's say that I've got 0.05 line pairs per millimeter. Okay? How thick is each line pair? Samantha.
It says.
If you need to borrow someone's phone to
Oh,
use a calculator, or
just what are we just dividing by?
so our line pairs per millimeter is 0.05. We need the inverse of 0.05. So how do you find the inverse?
So that whole.
1 divided by
That's
0.05.
0.0.
How do you find the inverse of 0.05, guys?
1 divided by 0.05.
Good. 1 divided by 0.05. Great. What do we get there?
100 by 5. 100 by 5, 20.
You get 20?
I think you saw
What do you think? What did you get, Samantha?
I got 20.
1 divided by 0.05 is 20? Okay. Anyone else?
Yes.
20? Very good. So, if our spatial frequency, right, is 0.05 line pairs per millimeter, each line pair, the black plus the white, is 20 millimeters. Now, if I only want the black, or if I only want the white, what do I need to do with this 20?
Divide by 2.
Divide by 2. So how thick is the black line?
10.
10.
And how thick is the white line?
10.
10. So this one is 10, this one is 10.
Oh.
Does that make sense?
I just didn't know how to
Don't
begin
ask
it.
me tomorrow.
So the first number, 0.05,
Mhm.
is
Line pairs per millimeter. How many line pairs you can fit inside 1 millimeter? So, the bigger this number is, the smaller your lines are, right? Because as things get smaller, you can fit more stuff in the same space. So, let's say that instead of 0.05, we now have 0.5. If we have 0.5 line pairs per millimeter, how thick is our line pair?
2.
Okay, I'm seeing 2, I heard 2. Johns, what do you think?
I want to say it would be 2.
2? How did you get 2?
Just move the point over.
Uh-huh.
So I know 0.05 is 20.
Oh, okay.
Oh, come on, John.
So you moved the point over for both of them?
Yeah, basically.
actually the answer.
Or I'll just stay right now.
Answer it. Don't look. Right, so yes.
Yeah, it is true.
It is 2. Very
That's
good.
fun.
So 1 divided by 0.5 gives you 2, right? So together, black and white is 2 millimeters. So how thick is each one? 1 millimeter per each, right? 1 millimeter for each of them. Great. So, right? If we have a lot of line pairs per millimeter, right? 10 line pairs per millimeter, how thick is each line pair?
1 by 10.
1 over 10.
And
So
this is 0.1.
good. So 0.1 millimeters for black plus white. So how big is each one individually? Divided by 2. 0.05 millimeters, right? 50 microns. So does that make sense,
Now it
Veronica?
It does, but
It does?
you don't process.
Okay, so would you like to try one then? For example, let's think of a number. Let's say that we had 0.2 line pairs per millimeter. If we have 0.2 line pairs per millimeter, how thick is each line pair?
5.
All right. So, 2 line pairs per millimeter. Okay, so how did you get 5?
1 divided by 0.2.
Good. 1 divided by 0.2 does give you 5, so it's 5. Right? So 5 millimeters.
And then you have 2.5 lines.
Good. So black line is 2.5 millimeters. How about the white line?
2.5.
How about the white line, Veronica?
2.5.
Also 2.5. Very good. Great job. Right, so just do 1 divided by line pairs per millimeter to find the thickness, and then divide by 2 to find each individual line. Okay, Reagan?
Where should my kid go?
All right.
Can we just meet you in the restaurant?
Okay, you want to check out what we've got so far?
All right, well, we are pretty much at the end of our time here, so we will go ahead and stop here for today. Next class, we will finish